Okay, this is our first screencast for IB Physics SL and HL, and it deals with kinematics. Okay, so this is to be the first module in the first topic for the IB exam. Okay, the first thing is that the definition of kinematics is it's the expression of the vector motion of any object undergoing a constant acceleration over a time interval. Okay, so it deals with constant acceleration. We're not going to do anything this year that involves changing accelerations or constantly changing acceleration. That is a calc-based problem. We will do situations where you will have a constant acceleration that will change instantly into another constant acceleration, and we'll get to that eventually, but that is one thing to keep in mind. So we're only going to deal with constant acceleration. Now, kinematic expressions already take into account the net force, the driving, the retarding forces. You'll see in just a moment that there's no mention of forces anywhere. These really are the result of the net force. What happens because of a net force acting on an object. You guys learned in previous years that when you have an unbalanced force on an object, it will accelerate in a certain direction. And that's what kinematics does. It lets you look at how the motion occurs and little nuances of it over time because of a net force. And then, so really, if we're saying that there's a constant acceleration, then we're also saying that there should be a constant net force. Once the net force changes, the acceleration changes, and then you have to approach the problem differently. Okay, but we'll get there. Now, one thing you have to understand, and if you ever are interested in hearing more about this, if you ever go to the MIT OpenCourseWare where you can watch physics lectures from Dr. Lewin, he talks about where everything comes from. All units and all variables, all physical factors come from length, time, and mass. Everything. Okay, every single thing that we're going to talk about for the next 2 years stems from length, time, and mass. They're all combinations of those three. Now, kinematics expressions that you're going to see in a moment only have length and time in them. There's no commentary on mass, shape, or density. Okay, so that means that when we use these equations, they can work for they can work for something small like a bowling ball, or you can use them for something very large like an airplane. Okay, so I want you to keep that in mind. Once you start getting at really, really high speeds, 50, 60% the speed of light, then the kinematics expressions kind of break down, and then you're talking something a little more relativistic. But that's for another topic later this year or possibly the beginning of next year. Okay? Now, here are the main quantities for kinematics. Okay, the first one is time. Now, time is represented by a lowercase t, and the base unit for time is in seconds. Alright, now there are possibilities of you doing other things with minutes and hours, but really you should always default to seconds. Okay. Now, something that you probably saw in algebra class, or you're going to see in calculus or math analysis, is that when you talk about the position of an object, you talk about it using s. Okay, so if you see a lowercase s in the equation in physics, that really represents the displacement or the position from the origin of the object. Okay, so if you have an s of positive 3 meters, that could mean that you are 3 meters to the right of the 0, 0 point. Okay, and again, the base unit for displacement position is meters. You could do things in feet, you can do things in kilometers, nanometers, something like that, but really when you're talking about larger objects, bowling balls, you're not talking about electrons or anything like that, you're talking about bowling balls, cars, people, you would use meters as your base unit, because that makes the most sense because of the relative size of the object and the movement. Okay. Now, a lowercase u is initial velocity. Okay, now last year we used VI and VF for those of you that had physics with me or Mrs. Dinger, and or Mr. Hobson even, or Mr. Daney, we used probably a VI. Now we're going to use lowercase u. Okay, so we don't confuse our VIs and our VFs or our V1s and V2s. So U stands for the initial velocity, the velocity at time 0 when you start looking at when you start to look at a situation. All right. Now, if you notice, it's measured in meters per second, coming from the meters and the seconds that we just talked about. But for IB purposes, they don't write it as a fraction. They always write everything in the numerator. So you should write it as, instead of meters over seconds, you should write it as meters seconds to the -1. Okay, and that's going to be true for all units that you write for the entire 2-year course. No matter what we're talking about, you want to put things in the numerator. Okay, so keep that in mind as we go. Okay, next thing, final velocity. Now, final velocity is just a V. Last year we may have written it as VF or V2, something like that, but now we're going to go with just V. So we're going to use U and V. Now, final velocity is also measured in meters per second. That should make sense. You always want your units to match, so try and keep them the same in meter seconds to the -1. Okay. Now, acceleration. Now, acceleration is defined as the rate of change of the velocity. It tells you how the velocity is changing. So if you're speeding up, your velocity is growing. So if your velocity is growing, you have something accelerating it. There's a net force attached to that object, causing it to speed up. Okay. The acceleration will tell you how many meters per second your velocity grows every second. So, for example, something that is in free fall has an acceleration due to gravity of 9.81 meters per second to the -2. Okay. Now that means that for every second that passes, that object will gain 9.81 meters seconds -1 of speed. Okay. And again, that could have different units, but we're going to stick with meter seconds to the -2 right now. Okay. So those are the base things. Now, what happens is they're used in different combinations and equations based on what you have. Okay, so we're going to go over those base ones for right now. Okay, now there are 3 main equations that you're going to find in the data booklet for the IB exam. Okay, you're allowed to use the data booklet anytime in class, anytime at home, and on the test. Okay, so you want to get comfortable with using these big 3 that you see right here. Now, the first one, if you notice, there's no A in the equation. It uses position, initial velocity, final velocity, and time. Okay, so that's a good one to use if you know things about the situation, but you don't know the acceleration, and you're not asked to find it. Okay, so if you had the position, the time, and the final velocity, and they asked you what the initial velocity of the object was, this would be a good choice because you have one variable and you have 3 nodes. Okay. Now the second one is missing final velocity. Okay, so it's missing the final velocity in this one, and if you notice, this is a polynomial. It's a quadratic. Okay, you can actually use the quadratic equation if you needed to solve for t. Okay, which might happen at some point in this first marking period. When we get more into this, you might actually have to use the quadratic equation to find the time. Okay, especially with projectiles and things that are launched vertically. Okay, but this is a good one when you don't have the final velocity. The last one looks a little different. This one has no time in it. Okay, it's not always clear what the time is of something that's in motion. So this one's a good one if you know about the speeds, you know about the acceleration, you know how far it went, right? So you have to look at these. You have to go by the givens and the knowns that you have and decide the appropriate one. Now, there's one thing I hope that you can see in a pattern of these 3 is that the initial velocity u shows up in all 3. If you're not asked to find it, you must know the initial velocity of an object in order to do anything. Okay. Now, sometimes it's kind of hidden in the question, like if it says an object's at rest at the beginning, the words at rest signify a initial velocity of 0, u equals 0. Okay, but you have to know the initial velocity if that's not the thing that you are asked to determine. So let's go through an example, and I'm going to show you all the work and everything. So take a moment and read over this. Jets at JFK accelerate from rest at one end of a runway and must maintain the takeoff speed before reaching the other end of the runway. If a plane starts from rest and can accelerate at 2.2, will a 2,000 meter long runway be long enough to reach the necessary takeoff speed of 95 meters per second? Okay, so that's kind of a, there's a lot of numbers in there. There's some hidden things in there that you can use. So what we need to do is we need to walk ourselves through the process of solving a kinematics equation. Now the process that we're going to use isn't going to change all year. Okay, if we're doing a force problem or we're doing energy, but you still go through the same steps. Okay, but I thought we should start off this way and do a specific kinematics example, so you have something to work with, especially those of you that didn't have physics as a 10th grader. Okay, so let's take a moment and let's go through it. So all I did up at the top here is I rewrote the question so you have something to reference as we walk through it. Now, the first thing is you want to make a list of your givens. You want to look at the problem, find those values that you could be useful to you, pull them out and make yourself a list. Now, I'm going to expect to see a list like this. I will expect a list of givens with variables, numerical values, and the units. Okay, that is an absolute must. Right? So there's a couple things that are obvious. Now the way you can figure out what they are, you go by units. If you see that you have a value of 2.2 meters per second squared, or meters seconds to the negative second, that unit automatically tells me that it's acceleration. Okay? You see a runway of 2,000 meters, you automatically know you have a displacement of 2,000 meters, okay, because of the unit. Now the one thing that's hidden in there is if a plane starts from rest. Well, if it starts from rest, that tells me that the initial velocity is 0. Okay, I will expect that you do this. I know some of you like to kind of skimp on your work a little bit. You can't anymore. You have to show everything. I can't stress that enough. Right? It's imperative that you show your work. I can't help you if I don't know what you did. Okay? So once you have your list of givens, you have to look at your equation choices. So you really have a couple equation choices. You have the 3 that we talked about, and also you have V equals S over T, the definition of velocity. So I put that on there. That should be a given to you. You should know what that is. Now, the way to go about this problem is you have to look at the things that you have. Okay? Look at the things you have on your list of givens and pick an equation that fits that list the best. Okay. Now here's what we got. If you notice, everything that's in the list of givens fits in. We don't have a variable left over in the equation that was chosen. Okay. I didn't pick the other 3 that had, because they have time in it, and I don't need to know the time. I'm not looking for the time. Right. So I picked the one that made the most sense with the list of givens I have. But if you look at this, I have V, U, A, and S. I have all of them. So if I plug in all 4 givens, I don't have any variable left over to solve for. All right. So this is how I'm going to approach it. Now there's always more than one way to approach it. I'm going to explain to you how I see it. Okay. Now if you have a different way and you want to run it by me, that's great. No problem. We can sit and talk about it. So what I'm going to do, first off, I can take the u out because I know it's equal to 0. So I took the u out. What I'm going to do is I'm going to solve for s. I'm going to solve for the displacement it takes to reach 95 meters per second of velocity. Because I know I have to reach a speed of 95 meters per second in order to take off. So if I can figure out how much distance that takes, s, if I can take that and find out what s is and compare it to the amount I have available of 2,000, then I'll know whether I made it or not. So I'm going to look at it as I'm going to figure out what distance it takes to reach 95 meters per second, and I'm going to compare it to the 2,000. So if you notice what I did, I solved for S first. Okay, so I did my work, I did my algebra, I solved for S, and then I put numbers in. Okay, so once I did that, and if you notice, I also put units in. Okay, so I put units in my work. Right? Now, the stuff that's written in red, italicized, you don't have to write that out. I'm doing it for the purpose of you seeing what happens. Okay? I do not expect you to write out the words on the right. Okay, the one in what's in red. I will expect to see what is written in black. Okay? I expect to see your givens. I'm going to expect to see the starting equation, v squared equals u squared plus 2as. And then I expect to see you solve for the variable before you put any values in for them. Okay? So the second line that says v squared equals 2as, you could skip that and be okay. But I expect to see the starting equation, I expect to see you solve for the variable, and then I expect you to see the numbers put in before you give me your answer. Okay? Now, let's look at this. I have an answer of 2051.36, but if you go back to your work, I have two significant figures in the two numbers that I use, 95 and 2.2. So I have to make sure my answer matches that. So I have to change my answer to 2100 meters based on the significant figure rule. Okay? So if I have an answer of 2100 meters, is the runway long enough? No. Okay, I need roughly 100 meters of extra space in order to reach the 95 meters per second in order to take off. So I won't make it. Okay? Now, I want to see that. I want to see that you wrote a number down, and I want to see how you convert it to the right sig figs. Okay, I'm okay with you doing that. You don't have to go right to the sig figs, but your final answer, which you should circle or highlight or something like that, should always have the right number of significant figures in it, just like you learned in chemistry last year. Okay, so that's the steps. That's the process in which I would want to see you do a problem. Okay, givens, starting equation, solve for the variable, plug in the numbers, answer with the right number of significant figures. Okay, that's what I would expect, regardless of what type of problem it is. If it's a force problem, an energy, if we're doing quantum mechanics, I don't care. It has to have those major components. Okay? And so just to recap on what you guys just did, take notes on this process. Go back, watch that again, write down the steps that I highlighted. Okay, write down the example problem in your notes so you have something to reference. Okay, just in case you don't have internet access available, and also it helps to write it down in your own handwriting and make notes to yourself about little things. What does at rest mean? Okay, how you have to have all your units have to have everything in the numerator. Okay, little things like that. You take the time and write it all out. Another thing you notice is that the acceleration was constant. The acceleration of the plane did not change. Once the acceleration changes, then you have to do a completely different equation for that portion. So if I were to say that the airplane accelerated at 2.2 meters per second squared for 10 seconds and then moved at a constant velocity where the acceleration is 0, I just turned that problem into two equations. You'd have to look at it in terms of the first 10 seconds that has an acceleration of 2.2, and then you'd have to pick an entirely different starting equation and do an entirely separate piece where it has an acceleration of 0. Okay, so we'll do those in class, but you have to keep it in the back of your head because once the force changes, the situation changes. And our last thing is that these equations can be applied to vertical motion. So remember that, because once we get done with this first module that deals with horizontal kinematics, we're going to look into vertical kinematics, which is things in free fall, things getting launched vertically upward. You'll notice that the equations are exactly the same. You just will always know what A is. You will always know that A is equal to little g, lowercase g, excuse me, which is 9.81 meters per second squared down. Okay, so I encourage you to look over this again, rewatch it, put put a link somewhere that you have it easily available, because this is going to be helpful to you over the next few weeks as we go through kinematics and as we start getting into forces. Because once we get into forces and you find the net force, you can use the net force to find the acceleration and then use kinematics to find where the object is, how fast it's going, things like that. So this is going to start building more and more. This is a good base for us to start on, because we'll be able to use it in momentum, we'll be able to use it in energy, we'll be able to use it in forces, we'll be able to use it all year. Okay?